So the binomial probability distribution is defined and uses factorials. So n factorial is defined to be the product of the n integer. So for example, if we want to take a look at 5 factorial, then 5 factorial is just taking 5 times 4 times 3 times 2 times 1, which is equal to, well, 5 times 4 is 20, 20 times 3 is 60, times 2 is 120, times 1 is 120. So this is equal to 120. So if you have your calculators out, the calculator will compute the factorial for you. So for example, if you wanted to compute 10 factorial without having to do this manually, if you'll just take your calculators and type in 10, and then go to the math button, and then across the top you should see an option that says PRB. So if you'll arrow over to the PRB, that's all the probability stuff. And then you should see, I think it's menu option 4. Okay, so press 4 and then enter. So then you have 10 factorial, which is a pretty good size number. So just for funsies, if you will, and then I'll tell you why you computed this, because it's going to answer a question that you've always wondered your entire life. But if you compute 52 factorial, so you probably get a number that says, what's the first digit? 8 point, then there's a bunch of dot, 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 but then at the end it says E, like 67. Yeah. So about 8, and then E67. So remember, that means you got to take the decimal and move it to the right 67 places. So can we agree that that's a really huge number? That's the number of ways that you can shuffle a deck of cards. I know you were wondering that your entire lifetime, and now you know. 8 times 10 to the 67th power. There's a lot of ways to shuffle a deck of cards. All right, the next item we'd like to take a look at then is the binomial coefficient. So if you've already taken a college algebra course, you have already been introduced to the binomial coefficient. The binomial coefficient, the way I read this, is n choose x. And that's the way I would like for you to refer to this when you communicate. So it's n choose x. And notice that this binomial coefficient is defined in terms of factorials. So for example, by hand, if we wanted to compute, say, 6 choose 3, then using the definition here, we would say that this is 6 factorial. So everywhere I see an n, I put the 6 in, divided by 3 factorial times 6 minus 3 factorial. So this is going to be 6 factorial divided by 3 factorial times 3 factorial. All right, so then by definition, 6 factorial is 6 times 5 times 4 times 3 times 2 times 1 over 3 factorial, which is 3 times 2 times 1, and then another 3 factorial, which is 3 times 2 times 1. Okay, so by arithmetic, I could take this 3 times 2 times 1, which cancels out with that 3 times 2 times 1. And notice that this 3 times 2 times 1 is 6, which will cancel out with this 6. So at the end of the day, we're just left with 20. Okay. So some other ways that you can see this written would be NCX. Sometimes they use R instead of the X. Okay. Okay. So if you want to use your calculator then, if you will enter if we want to compute this via the calculator, first you enter the 6, and then again if you go math and then go over to the PRB, I want to say that it's about menu option 3 or 2? 3? Yeah, so choose menu option 3, NCR, and then enter the number 3, and then press enter. So that's how we can compute these things via technology as well. So if you don't, you're forced to crunch this by pencil and paper. That's how you would do it. You just write these things out and then start canceling denominator and numerator, and then boom, you're right there. So the basic idea that generates this n choose x is a counting technique that was discussed in chapter 4, but we didn't discuss it, but I'm just going to give you kind of the highlights and the down and dirties. So there's 2 types of counting techniques. One is called a permutation and one is called a combination. And that binomial coefficient n choose x is a combinatorial or a combinametrics way of using a counting technique, and that counting technique is used when order doesn't matter. So when I say order doesn't matter, is if I were to pick 3 people from the classroom, just randomly pick 3 people, say Bathsheba, Stephanie, and Cheryl, and all I want to do is just pick them, well, would that be the same way as picking Stephanie, Cheryl, and then Bathsheba? Again, I'm just needing 3 people, and I don't care how I get them. I just want them. So order is not going to matter. So here's another thing for those of you that like to go gamble. My question to you is, suppose you're playing poker, and you're dealt your 5 cards, and you pick them up and you look at them. After you get your 5, you pick them up and look at them, and you're like, aha. And you observe that you have the ace, king, queen, jack, 10 of diamonds, which is a full house, which is the highest hand on the face of the planet. So my question to you is this: do you care how you got the cards, or are you just happy that you got the full, did I say full house? Royal flush. Sorry. Ace, king, queen, jack, 10 is not a full house. It's a royal flush. Sorry. I think I said that. But my question is, with the highest hand of the royal flush, do you care how you got the ace, king, queen, jack, 10? Or are you just happy that you got them? You're happy that you got them. So that's when we say order doesn't matter. You just want to get X objects from a group of N objects. So let's take a look. Suppose you borrow 4 famous paintings, or suppose that you own the 4 famous paintings, and a museum wants to borrow any 2 of your paintings for a showing. How many ways can this be done? Well, again, you own 4. The Denver Art Museum wants any 2 of them, and they don't care which 2 that you have or which 2 that you give them. So here, order doesn't matter. So then you know that you're going to use this binomial coefficient. So you know that you're going to come over here and compute 4 choose 2. And when you compute this, you should come up with 6. So kind of well, I was going to go through and actually itemize all of these, but I don't think I will. Suppose that you and your spouse decide you're going to have 3 children. Of the 3 children, how many ways can you have 2 girls? So again, having 2 girls out of the 3, you know that you can have a girl, girl, boy, girl, boy, girl, 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 boy. So there's 3 ways to do that. But in a combinatorial way, you're going to say, well, I'm going to have 3 children, or we're going to have 3 children, or she's going to have the 3 kids, however you want to view it. And from those 3 children, you want 2 girls. So that means that there is going to be 3 choose 2 ways of doing this. So again, this is just going to be 3 NC2 or NCX2, which is going to equal to 3. A committee consists of 5 professors, A, B, C, D, E. How many ways can an ad hoc representative committee of 3 be formed to attend the conference to represent the department? So in this case, again, how many professors are, so this is the thought process. How many professors are there? 5. How many of them do you want? 3. Does it matter how you get them? No. So you know this is going to be 5, choose 3. So if we compute that, and if you want to verify, so this is 5 NCX3, should come up with 10. Okay, so this kind of lays a little bit of our foundation down. I'm going to come back to the binomial coefficient here in a little bit. But to go to the next step, a binomial experiment has 4 assumptions that need to be met. And if there's a violation of any of these 4, then the binomial distribution cannot be used. So first, there has to be a fixed number of trials. And that's going to be your n. Second, each time the experiment is performed, there can only be 2 outcomes, which is usually denoted as a success or a failure. Depends on how you define a success. So again, going back to my opening examples, remember I talked about flipping a coin? I said, suppose that you flip the coin 20 times, there's your n. There's only 2 outcomes, heads or tails. Going back, take a look at our drilling for oil. Said you're going to go out to the oil field and drill 10 oil wells, I believe I said 10. And there's only 2 outcomes. You're either going to strike oil or you're not going to strike oil. If you'll recall the president issue one, you're going to go out and ask 50 people, so there's your n. And there's only 2 outcomes if you phrase the question correctly. Do you currently approve of the way President Obama is handling the education issues in this country? Somebody's either going to have to say yes or no. So there's only 2 outcomes. Third, that the n trials are all independent. So again, going back to the coin flipping example, each time you flip the coin, the outcome of each flip is independent. That is, the outcome of the previous events do not have an influence on the outcome of the next event. If you do things correctly on the presidential issue, I'm not asking if you can't ask like a husband and a wife or a family unit, but if you were to go down and just stroll along the 16th Street Mall and just say, hey, can I ask you a question? Do you approve of the way President Obama is handling education issues in this country? They're either going to say yes or no, and then you go down to the second or third person, more than likely their answer and the other answer will not have an influence. So you have to have independence. And then finally, the probability of the success, depending on whatever that probability is, has to remain constant for each of the n independent trials. So notice if I flip a coin, the probability of and if I define a head to be success, then the probability is going to be 1/2, and each time I perform the experiment, it's going to be 1/2. If you go out and take a look at the Gallup poll and use their information, then I don't even know what his rating is lately, so I'm just going to say around, does anybody know off the top of their head? I want to say 53% that's because I checked that last semester, but let's just run with 53% approval rating. So that means that if you go down and ask somebody, then each time you ask somebody independently, then we can use that 53% to say that they will agree with the way that the president is handling particular issues. So the probability then remains fixed and constant and independent. Okay, so those are the four things that have to be met. So fixed number of trials, only two outcomes, independent, and the probability of a success or even a failure remains fixed and constant for each of the n independent trials. So now let's kind of motivate, I want to motivate the binomial distribution. So according to the 2010 New York Times Almanac, the percent of deaths related to HIV/AIDS is 0.035 in 2004. Suppose we randomly choose 3, that how should be a who have HIV/AIDS. What is the probability that 2 have survived? Okay. So I'm actually going to go through and itemize all of this and then show you how the formula is going to come out. Oops, thought I fixed this up. All right. So here's the idea. Survived. Okay. So here's the idea. If I take a look and if I draw and if I decide to choose three people and ask 3 people who have, you know, HIV/AIDS or whatever, and there's a general pool out there, there's the following events can happen. We can either have 3 successes, meaning they survived, or I could have a success, success, failure, or I could have a success, failure, success, or a success, failure, failure, or I could have a failure, success, success, failure, success, failure, 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 success, and all 3 didn't make it. Okay? Now, by independence, I know I could take the probabilities and multiply them together because that's what we do when we have independence. Again, going back to chapter 4, if 2 events are independents, then the probability of A and B is the probability of A times the probability of B. So here, when I take a look at 3 successes, I'm taking a look at the probability of survived and survived and survived. So by independence, then, I can product all of these probabilities. So this is going to be 0.035, 0.035, 0.035, which is going to be 0.0004. I need one more 0 in there. 0.0004. So here, if I have survive, survive, failure, then again, would you agree this is going to be, help me out here, 0.035 times 0.035, I'm not hearing everybody, times, and I'll give you a hint, this is 1 minus 0.035, so that's going to be 0.965. Which is going to be 0.001. So here I have a success, failure, success. So this is going to be 0.035. The failure is going to be 0.965 times 0.035, which is the same. For this one here, I'm going to have 0.035, 0.965, 0.965. And this is going to be 0.033. For this one, I get 0.965 times 0.035 times 0.035, which is going to be 0.001. For this one, we're going to get 0.965, 0.035, 0.965, which is going to be 0.033. For this one, 0.965 times 0.965 times 0.035, which is going to equal to 0.033. And then finally, 3 failures is 0.965, 0.965 times 0.965, which is going to be 0.899. Okay. So now we have to take a look at the following. If I want to take a look at out of three randomly selected people out of the AIDS/HIV pool in 2004, okay, from the 3 that I randomly select, 2 of them survived. So if I take a look at my sample space here, so we need to find where the 2 survivors are at. So here's one, and here's one. So the idea then is that the probability that 2 people survive out of the 3 then, would you agree that I would just add these 3 up? And notice that out of all this 8 options right here, right? If I add these 3 up, then I'm going to take 0.001 plus 0.001 plus 0.001. And would you agree with me that this is the same as 3 times 0.001? So far, so good? But now let's go backwards and take a look. Would you also agree with me that this is 3 times, and if I come over here and take a look at these, notice that I have 0.035 times 0.035 times 0.965. So in other words, I could come over here and write that this is 0.035 times 0.035 times 0.965. Like that. So far, so good? You don't need to write this down. Just follow along. I'm going to come to a grandiose result here in about 2 minutes. Okay, and that's what you want. And let's continue on. Just check me out here. Make sure you just follow along. So would you agree that this is 3 times 0.035 squared times 0.965? Okay. Now remember, this was a probability of a success. Let me get my pointer back up here to a darker color. So remember, this is a probability of a success, right? So, and then I have this multiplier of 3. So notice that I can kind of write this as 3, and now we're going to introduce some letters, p squared times 1 minus p. Okay. So now let's take a look. I went to the 2004 pool of AIDS/HIV infected people, right? And I picked 3 out of there. And from that 3, I wanted to know if 2 of them survived. You with me? Now, from that pool of 3, does it matter, does order matter on which two survived? No. So this 3 here comes from the fact that if I take n, and now that I don't care which order they come in, here's the orders right here. They're itemized for you. You can see them. And you can see that there are 3 of them. Right? So then I can take n, and then the ordering doesn't matter. So I could take n choose x from that pool of n. And then notice that the probability of the success then is p. And notice that this is p squared. Right? So this is p to the x, right? Look, notice that my 3 choose 2. Notice that this is x. That's the number of successes that I wanted. And notice that it came out here. I wanted 2 successes in this particular example. If I repeat this again and show you another thing, you'll find that this p is always raised to this x, the number of successes that you want. So p to the x, and then notice that this exponent is an exponent of 1. Well, if I have n people, 2 of them are going to survive. How many of them are not going to survive? 1. And how did you get the 1? So you took 3 minus 2. So notice again over here, if I take 1 minus p, then I can raise that because these are all my failures. So if I have n objects, I have x successes, then that must mean I have n minus x failures. Right? So this is n minus x. So now we get this guy. And that's the grand result right there. And that's how we get this formula. So let x denote the total number of successes in n Bernoulli trials with a success probability of p. The assumptions, again, these are the assumptions. 1, n trials are performed. 2 outcomes are possible. The trials are independent. And the success probability remains constant for all trials. Those are the assumptions that I talked about a few minutes ago. Then, to compute the probability that x is equal to x, using random variable notation, is equal to n choose x, p to the x, 1 minus p to the n minus x, which is the formula that we came up with. So the first thing you need to do when we're doing binomial probabilities, and this is how you can identify a binomial probability, is when you're reading the exercise and it says, suppose that you have 100 women participating in a pregnancy test and the results are 99% accurate, what is the probability that 25 of them will test positive? Notice 3 things were given. 1, n was given. 2, I gave you a percentage or a probability of a success. And 3, I wanted to know how many of them there were. Now, if you take a look at the previous probability stuff that we've been taking a look at, we've been talking about drawing cards, rolling die, things like that, or an empirical probability. Notice that all the exercises that you've worked thus far, up to this section, 5.3, have all dealt with things along those lines. They did not give you n, they did not give you a success probability, and they did not give you an x. Okay? So again, what I'd like for you to probably do over the weekend is to compare and contrast now Chapter 4 stuff we talked about, sections 5.1 and 5.2 information on a general discrete probability, and now the binomial, and take a look at the differences of the questions so that when I randomly hand you a question, you will know which type of a probability you're going to have to work with, because that's one of the biggest issues that I've heard about with the course is I don't know which one to choose. Okay, so now I kind of gave you the idea. So when you recognize a binomial distribution is characterized by two parameters, n and p. Those are the two things you need to know with a binomial distribution, n and p. And once you know n and p, everything else comes along for a ride, because you can make up the x as you go along. So you will know everything about the experiment once you know n and p. So a lot of times when we talk about a random variable now I can go back and I could talk about my random variable x, and then I could talk about my random variable x be distributed binomial with parameter n and probability success p. So two parameters, because later on we're going to get to the normal distribution and talk about the parameters to the normal distribution that will totally characterize that distribution. Okay? All right, so now let's talk about how to use this thing. What do you say? These out together. So a report on August 12, 2009, a Gallup poll reported that 53% of Americans approved of President Obama handling of educational issues. There's the website in case you're interested. At this rate, assume that we want to find that among 5 Americans, 3 of the Americans approve of President Obama's handling of education issues. So for part A, does this procedure result in a binomial distribution? B, if the procedure does result in a binomial distribution, identify the values of n, x, and p. Suppose there are 5 Americans. What is the probability that 3 Americans approve of the president's handling of educational issues? And then part D, what is the probability that at most 3 Americans agree with the president? So let's go through each one of these piece by piece. So does this procedure result in a binomial distribution? Remember, there are how many properties that we have to check? 4. So what's number 1? Number 1 is there's a fixed number of trials. Is there a fixed number of trials? Yes. What's the next one? Is there only 2 outcomes? So when you ask somebody, are there only 2 outcomes?
Yes.
They either do agree or disagree. There isn't any I don't know.
Why?
Because I said so. No, because it's got to fit the binomial here. And
Okay.
example exercise.
Okay.
Number 3, what do we have? Independence. So are the 5 Americans that you're going to choose, hopefully they will be independent. And then finally, number 4, does the success probability remain constant for the 5 Americans that you choose? Yes. So the 4 requirements are met. So the next thing, once you identify, notice the flow here, once you identify a binomial distribution, the next thing you want to know is what are n, p, and x. So n in this case is going to be what?
5.
Yeah, I heard you. 5? Thank you, Danny. X? 3? P? We're going to write this as a decimal. 0.53. All right, so suppose that there are 5 Americans. What is the probability that 3 Americans approve of President Obama's handling of educational issues? So for part C, this is asking us, what is the probability that x is equal to 3? So by our binomial probability, we know that this is going to be 5 choose 3, p to the x, 0.53 cubed times 1 minus p, which is 0.47, or you can write 1 minus 0.53, raised to the, and 5 minus 3 is going to be 2. All right. So to enter this into your calculator, if you will go something like this. You go open bracket 5 NCR3 close bracket 0.5 to the 3, 0.53 to the third, 1 minus 0.53 squared. So open bracket 5 math PRB menu option 3. So 5 choose 3. .53 cubed 1 minus 0.53 squared. Enter. So about 0.329. Okay. Yeah.
How did you get the 10.3 again?
Because it was given.
Oh, okay.
Well, you have to find that, the percentage, if it's not given.
If it's not given, then again, that's one of the assumptions, right? So part D asks us to compute the probability that at most 3 Americans agree. So how do I write this using random variable notation? So the probability that at most 3 agree. So how am I going to write it?
X is equal to less than 3.
Is less than or equal to 3?
Equals 5 over 3. Or 5 choose 3.
Okay, so but hold on. So this is the probability that, do we agree that that's how we're writing this? Got to make sure we're okay first. Okay. Now remember from our previous discussion, the probability that x is less than or equals to 3 means what? Means the probability that x is equal to 0, or the probability that x is equal to 1, or the probability that x is equal to 2, or the probability that x is equal to 3. So this is equal to 5 choose 0, 0.53 to the 0, 1 minus 0.53 to the fifth, all failures, plus 5 choose 1, 0.53, 1 minus 0.53 to the fourth, plus 5 choose 2, 0.53 squared, 1 minus 0.53 to the third, or 5 choose 3, 0.53 cubed, ran out of room, 1 minus 0.53 to the second. Right? Well, let's put it in and see what we get. What do you say? So now we get 5 math, 5 choose 0. 0.53 raised to the 0, 1 minus 0.53 raised to the 5th plus 5. Menu option 3, 5 choose 1, 0.53, 1 minus 0.53, raised to the 4th, I believe, right? So far, so good. 5, math, menu option 3. Oops. Math, PBR. What am I at now? 0, 1, 5 choose 0, 1, 2, 0.53 squared, 1 minus 0.53. Cubed. I think this is the last one, isn't it? 5. You guys getting this all down? 5 choose, where am I at? 3? 0.53 cubed. 1 minus 0.53 squared. Do I got them all in right? Yep, looks good to me. So 0.773 will be the probability that we have at most 3 people that will agree. All right, I think at this point in time, I would like to introduce a built-in routine so that we don't have to do this all the time. All right, but it is doable. All right, and if you will take a look at and press the stat button. No, I'm sorry, I lied. Distribution over here in yellow above the vars key, second distribution. And then if you scroll down, you're going to find a couple of options wherever they're at in your respective calculator. One of them is the Binomial PDF, and the other one is the Binomial CDF. So just to make sure we're all on the same page, and you can keep this in your mind, we will use Binom PDF when we are given the probability that x is equal to little x. That's what the Binom PDF does. So the Binom PDF will compute, so this guy will compute n choose x, p to the x, 1 minus p to the x. Or 1 minus p to the n minus x. That's what it'll do for you. So that'll compute this one right here. So if you will, let's just go ahead and take a second and compute this. So if I choose the Binom PDF, the Binom PDF takes 3 parameters. This function takes 3 parameters. And the parameters are easy to remember because they're in alphabetical order, NPX. So n in this case is going to be 5, comma, p is 0.53, comma, x was 3. Close it and then press enter and there's the answer. Same thing that we came up with when we manually typed it in. The Binom CDF stands for the binomial cumulative distribution function, The binom PDF stands for the binomial probability density function. The binomial cumulative distribution function, it's the idea of cumulative. So this is the part that's going to do all the adding for you. But you got to be careful because the Binom CDF will compute the probability that x is less than or equal to x. So you have to make sure that you have this form. Notice it has a less than and equals to. It does not have a greater than or equal to, and it does not have a strict less than, and it does not have a strict greater than. It only works this way. That's why it's very important for you guys to make sure that you write this stuff out and then pick the appropriate calculator routine or compute them by hand. Or you can go to the binomial tables in the back of your book and use the tables as well. Okay. So to compute this one, again, it's the same thing. Binom CDF NPX. And it will compute 0, 1, 2, 3, 4, 5, 6, 7, ... all the way up to x and sum them up for you. That's what this routine will do for you. So if we enter this into here, then we go second distribution, scroll down to binom CDF, n is 5, comma, p is 0.53, comma, and x is 3. And notice we get the same thing, 0.773. Okay. All right, I'm going to jump ahead to this one. According to the Harris poll number 49 on August 18th, 1999, 36% of adults stated they were afraid of snakes, and snakes topped the list of fears among adults. So if you're interested, there's the address. If 10 adults are selected, what is the probability that there are exactly 5 adults in the sample who are afraid of snakes? There are at most 3 adults in the sample who are afraid of snakes. There are at least 3 people in the sample who are afraid of snakes. So let's take a look at these individually. So for part A, we want to write this using random variable notation. So first, how am I going to write this using random variable notation? I'll wait. How do I write this using random variable notation? So P of x equals 5. Okay. So is this going to be a binomial experiment? Well, are there a fixed number of trials? Yeah. Do I have a probability of a success? Yes. Okay. And are they independent? Yes. And does the probability of a success remain the same? Yes. So the probability that x is equal to 5. So am I going to choose binom CDF or binom PDF? So I'm going to choose binom PDF. And it takes 3 parameters, n, p, and x. So n is 10. N is are you guys serious? N is, I just want to make sure I'm getting everybody in on the game here. P is 0.36. X is
5.
5. This is button pushing. I'll let you take care of the rest. How about part B? There are at most 3 adults in the sample who are afraid of snakes. So how am I going to write this using random variable notation? How am I going to write this using random variable notation?
P.
3. So, am I going to choose Binom PDF or Binom CDF? CDF. And is this in the appropriate form for the CDF? Yes. So, Binom CDF takes 3 parameters, n, 10, p,
3.
comma, x is
3.
3. Again, this is button pushing. I'll let you do it. C. There are at least 3 people in the sample who are afraid of snakes. So now we need to write this using random variable notation. Think about it for a second. So, there are at least 3 people. So using random variable notation, how can I write this?
P. Bracket. X. Greater than.
So x is greater than or equal to 3. Now is this in the correct form for you to do your button pushing? No. So how do I get this into the form x is less than or equal to little x?
3 is less than or equal to X.
You're close. 3 is less than or equal to x.
Or X is less, right.
This is where we're going to use, if the probability that x is greater than or equal to 3, then I'm going to have to flip that inequality sign. Do you agree? But in order for me to flip that inequality sign, I have to use what kind of probability? Or I'm going to have to use one of the rules we talked about back in chapter 4. I'm going to have to take the what? But I'm going to have to take the, I'm looking for a particular word here. And I'll give you a hint. It begins with a C. The complement. So the probability that x is greater than or equal to 3 is equal to 1 minus the probability that x is less than or equal to 2. 3 is included over here. So now this is 1 minus binom CDF NPX.